If you look up at the night sky and think that what you see is already vast, then you are probably judging the universe in the way the human brain is accustomed to, comparing with the eyes, with intuition, with distances that can still be imagined. But the universe does not operate on that intuition. Out there exist structures so large that light needs more than 1 billion years to cross them. Tonight, we will move from the most familiar distances to the largest thing humanity has ever discovered in the entire universe. Before talking about the largest thing ever found in the universe, there is one important point that needs to be clarified from the start. What we actually mean by large, not in the scientific sense, but in a very everyday, very human sense. What your brain perceives as large is shaped by the spaces you inhabit each day, places you can enter, move through, and leave with your own body. Imagine an outdoor playground, the kind commonly found in residential neighborhoods in the United States. A small area with a slide, swings, a few benches, and a low fence around it. Children can run from one end to the other in under a minute, and an adult can take in the entire space at a glance. Our brains are very good at understanding places like this, because we can encompass them in a single view and associate them with familiar sensations of movement and time. Expand that a little further and think of a typical city block. A row of buildings, a few intersecting streets, a grocery store on the corner, maybe a small cafe. You can walk across the entire block in a few minutes, and after passing through it a few times, you begin to visualize it as a complete whole. Spaces like this form the first units of measurement for our intuition about size. Go farther still, to a large neighborhood or an urban park, and the sense of scale begins to change. But it remains manageable. You know, it might take 10 or 20 minutes to walk across, or just a few minutes by car. Even though these spaces are much larger than a playground or a city block, they are still tightly connected to human rhythms, to spans of time the body can directly experience. Even when we talk about an entire city, the human brain still has a reference point. You know, a city may stretch for dozens of kilometers, and traveling from one end to the other can take hours, but you have done it, or at least know someone who has. So it remains within the realm of what can be imagined. A city, no matter how complex, is still a space a human being can live inside for an entire lifetime. The problem begins when we leave spaces designed for humans. Seen from above, Earth appears enormous, but in reality its circumference is only about 40 kilometers. If you drove continuously at highway speed without stopping, you could circle the Earth in roughly 2 weeks. 2 weeks sounds long, but it is still a length of time the human mind can grasp. Everything changes when we step beyond Earth. The Moon, our only natural satellite, lies about 384,000 kilometers away. That distance is large enough that you could line up all the planets of the solar system between Earth and the Moon and still have room left over. Apollo missions traveled far faster than commercial aircraft, and even then, the journey took more than 3 days. 3 days just to reach a place that, in astronomical terms, is considered very close. And this is the first sign that our intuition is starting to fail. Because 3 days, long or short by human standards, is utterly insignificant on the scale of the universe. Then comes the Sun, the central star of the solar system. It lies about 150 million kilometers from Earth. And if you tried to imagine making that journey by car at highway speed, it would take roughly 170 years. Not a single human lifetime, but many generations back to back. At this point, the human brain has almost nothing left to anchor its intuition. We did not evolve to understand numbers like these. Your brain is optimized to remember paths through forests, to estimate the distance between you and a threat, to decide whether you should run. It was not designed to process hundreds of millions of kilometers or centuries of continuous travel. Once numbers pass this threshold, intuition collapses. To go farther, we are forced to change how we measure distance. Instead of vehicles or familiar speeds, astronomers use light as a ruler. Light travels at about 300,000 kilometers per second, so fast that in everyday life, you almost never notice any delay at all. But over cosmic distances, even light needs time. Light from the sun takes about 8 minutes to reach Earth. That means when you see the sun, you are seeing it as it existed 8 minutes ago. If something were to happen on the sun's surface right now, you would only know about it 8 minutes later. At cosmic scales, distance and time begin to merge into one. This is why a special unit of measurement exists: the light year. A light year is the distance light travels in 1 year. Nearly 9.5 trillion kilometers. This number was not created to make humans feel comfortable, but to make it possible to talk about the universe without resorting to endless strings of digits. The closest star system to the solar system, Proxima Centauri, is about 24 light-years away. That means the light you see from that star left it more than 4 years ago, wandering through the darkness of space all that time before reaching your eyes. Even the nearest things in the universe are separated from us by years of light. Within roughly 15 to 20 light-years of Earth, there are several dozen other star systems. On astronomical maps, these are considered close neighbors. But in the context of the universe as a whole, this region is so small it is almost negligible, like a tiny corner of a playground inside an infinitely vast city. If, at this point, you feel your intuition starting to waver, that is exactly what should be happening. Because to talk about the largest structures ever found in the universe, we must accept that familiar human units of measurement no longer work. We are forced to learn how to think on an entirely different scale. And one crucial thing to remember is this: we are only just beginning. The distances mentioned so far, though far beyond everyday experience, are still only the lowest steps in this story. Each step that follows will make everything we have discussed seem even smaller. From here on, the concept of large will no longer resemble anything you have ever imagined before. Up to now, we have been talking about distance in a relatively familiar way, even as the numbers stretch far beyond daily experience. But there is one critical transition we have not yet fully crossed, and without it, everything that follows would feel disconnected. It is the moment when you realize that in the universe, distance is not just space. It is also time. In everyday life, distance and time are separate concepts. You can stand still while time passes, and you can travel far while time passes quickly or slowly, depending on the means of transport. But on cosmic scales, these two concepts begin to merge in a way that leaves human intuition nearly helpless. Consider a very simple situation. When you turn on a light in a room, the light reaches your eyes almost instantly, so fast that your brain registers no delay at all. The distance is too small, and light is too fast, so time seems to vanish from the equation. But that is only because you live in a world that is very small compared to the universe. When you look up and see the sun, you are not seeing it as it exists right now. Light from the sun takes about 8 minutes to cross the space between it and Earth. This means the image you see is always 8 minutes behind reality, and there is no way around that. No matter how advanced your telescope may be, 8 minutes may sound trivial, but it carries an extremely important implication. It tells us that every observation of the universe is an observation of the past. There are no exceptions. There is no way to see the universe live in the present moment, because light always requires time to travel. When you look beyond the sun, That delay increases rapidly. The stars you see with the naked eye in the night sky are typically several years to several tens of years away in light travel time. Their light left the stars when you were still a child, or even before you were born. Tonight, you are looking at a sky that no longer exists in a literal sense. Some of the brightest stars in the sky lie hundreds of light years away. When their light began its journey toward Earth, our planet was in a very different chapter of its history. Events you consider ancient, in human terms, are, for that light, only a very recent moment. This leads to a very strange consequence. The farther you look, the deeper you are looking into the past. There is no time machine here. No science fiction. There is only light, moving at a finite speed, carrying information from moments that have already passed. Telescopes are, in essence, machines for looking back into history. This is also why astronomers do not say that an object is simply far away, but instead say that it is so many light years away. That number does not only tell you the distance, it tells you when in the history of the universe you are seeing it. A galaxy 1 million light years away is observed as it existed 1 million years ago. At this point, a reversal in the way we think begins to occur. In human life, time is usually fixed, and space is what we move through. But in the universe, space itself determines the time you are observing. An object's position in space is also its position along the timeline. When astronomers observe very distant galaxies, they are not only seeing objects that are far away, they are seeing the universe at a much younger stage. Those galaxies look different, smaller, more chaotic, because the universe at that time had not yet had enough time to form the stable structures we see today. Each distance is a slice of history. This means the universe never appears to us as a complete picture. When you look at a large region of space, you are seeing many different moments at once. Objects close to you represent a relative present, while objects farther away represent a deeper past. Imagine looking at a city stretching across dozens of kilometers, but light from each area takes a different amount of time to reach your eyes. The nearby district shows images from a few minutes ago, while a more distant area shows images from hours ago. The scene you perceive is a layering of time, not a single moment. On cosmic scales, this effect becomes extreme. When astronomers observe a structure stretching hundreds of millions of light years, they are seeing different parts of that structure at different stages of development. There is no way to freeze time and view the entire thing at the same instant. This is one reason studying the universe is both powerful and difficult. Powerful, because distance allows us to infer evolution over time. Difficult, because what we see is always a mixture of many different moments. Yet this very limitation gives us a unique tool. By comparing objects at different distances, scientists can reconstruct the story of how the universe has changed. Looking nearby is looking at the present. Looking far is looking into the past. And looking extremely far is looking at the opening chapters of cosmic history. By now, you may be realizing that we are no longer just talking about how far away things are. We are talking about how the universe stores its own memory in light. Each photon is a piece of information, carrying an image of a moment long gone, traveling through space for millions or billions of years. And this leads to an even deeper implication. When we talk about the largest structures in the universe, we are not only talking about their size in space, we are talking about structures that extend not just across space, but across time. They exist as processes, not as static objects. From this point onward, everything we discuss will always involve two parallel questions: how large something is in space, and when we are seeing it in the history of the universe. These two questions cannot be separated. Ignore either one, and the picture will never be complete. We have left behind the world where distance is just kilometers and time is just the clock on your wrist. We are entering a world where looking far means looking into the past, and where the present, in an absolute sense, almost does not exist. This is the foundation required to understand the immense cosmic structures we are about to discuss. Because when we finally talk about galaxy networks stretching hundreds of millions of light years, what matters is not only how large they are, what matters is what story they tell us about the universe's past, and about our place within that timeline. And to continue, we must clearly establish one thing: where we stand within the entire picture. If you could fly away from Earth, far beyond the Milky Way, and then keep pulling back hundreds of millions of light years, a very strange moment would occur. Galaxies would no longer look like isolated islands. They would begin to arrange themselves into curves, long strands, with vast, dark regions between them that appear almost empty. This is not an illusion, and it is not your eyes deceiving you. It is the true shape of the universe on its largest scales. For much of the 20th century, many scientists believed that if you looked far enough, the universe would appear nearly uniform, with galaxies scattered evenly like grains of sand on a beach. But as sky surveys began to cover millions of galaxies, that assumption slowly collapsed. Instead of randomness, a strange order began to emerge. Galaxies are not evenly distributed. They gather into elongated strands, stretching across space, intersecting at especially dense nodes. These strands are called filaments, and they are the fundamental components of what we now call the cosmic web. Each filament can span hundreds of millions of light years, containing thousands of galaxies, along with hot gas and vast amounts of invisible matter. Where filaments intersect, gravity becomes so strong that galaxy clusters form, the largest gravitationally bound structures the universe has ever created. Between the filaments lie regions that are entirely different in nature. These are called voids. Cosmic emptiness. In large voids, matter density may be only 10 to 20% of the cosmic average. If filaments are crowded cities, voids are deserts stretching across hundreds of millions of light years. What is remarkable is that the cosmic web was not designed. No one planned it. It is the result of a natural process unfolding over 13.8 billion years, beginning with incredibly small irregularities in the early universe. When the universe was very young, matter was distributed almost uniformly, but almost does not mean perfectly. Observations of the cosmic microwave background revealed density fluctuations so tiny they seem implausible. Only about 1 part in 100. Ling, ling, ling. Yet those minute differences determined the entire structure of the universe that followed. Gravity ignores no imbalance. Regions that were slightly denser began to pull in more matter, becoming denser still. Less dense regions lost matter and grew emptier over billions of years. This process amplified itself like a small ripple, gradually becoming a powerful current. The final result was not isolated spherical clumps, but elongated streams of matter connecting dense nodes. This is how filaments were born, and how the cosmic web took on the shape we observe today. At the center of this story is dark matter. About 27% of the universe's total mass energy is dark matter, while everything you can see, stars, planets, people, accounts for only about 5%. The remainder is dark energy, which is driving the universe's accelerating expansion. Dark matter does not emit light and does not interact with it, but it interacts strongly through gravity. It was dark matter that collapsed into filament-like structures very early on. Even before galaxies formed, ordinary matter later fell into these frameworks, cooled, and formed stars. Remove dark matter from the picture, and the cosmic web would not exist. Galaxies could not hold their shapes. Clusters would fall apart, and the universe would look entirely different. The cosmic web is, in essence, a map of gravity drawn over billions of years of evolution. Because we cannot observe dark matter directly, scientists rely on indirect methods. One of the most important is weak gravitational lensing, where light from distant galaxies is subtly distorted as it passes through regions containing large amounts of invisible mass. These distortions are incredibly small, but when measured across millions of galaxies, a clear map emerges. These maps show that the cosmic web is not an abstract concept. It is a real physical structure that governs the motion of galaxies and the flow of matter on the largest scales. Galaxies do not move randomly. They stream along filaments, pulled toward nodes where galaxy clusters reside. The cosmic web is not static. In the early universe, filaments were short and faint. Over time, they thickened, stretched out, and their intersections grew denser. Today, some of the largest filaments extend more than 500 million light-years, linking regions of space separated by almost unimaginable distances. Voids evolve in parallel. As matter drains away, they expand, becoming regions that are nearly empty. The largest known voids span about 300 million light-years in diameter, yet contain only a few dozen galaxies instead of the thousands found in matter-rich regions. This leads to a crucial realization. The cosmic web is not only the largest structure in the universe, it is also the natural limit on how large structures can be. Matter cannot bind together indefinitely, because the universe has a finite age and space itself is expanding. For many years, astronomers believed the cosmic web imposed a clear upper limit on size. Filaments hundreds of millions of light-years long made sense. But beyond a certain scale, physical connectivity would become tenuous, or cease to exist in any strict sense. That is why every time a largest structure ever discovered is announced, the scientific community responds with careful questions. Is it truly a physically connected structure, or merely a coincidence of positions? Has it been confirmed using multiple observational methods, or does it rely on a single type of data? These questions are not cynical. They are how science protects itself. And through this process of scrutiny, several famous structures have been announced, debated, and later re-evaluated. From here, our story begins to move closer to its critical point. To understand why a new structure caused such a shock, we must look back at the previous records, the Great Walls that sparked years of scientific debate. Only with that context can you see why the next name is not simply a larger number. Before the name Quipu appeared, astronomers had already thought many times that they had reached the limit. Each time cosmic maps expanded, a new structure emerged, larger, longer, and more challenging to our intuition about how matter can organize on the largest scales. These structures were often given a vividly descriptive name: Great Walls. The Great Walls of the universe. The first time humanity truly realized that galaxies could arrange themselves into colossal structures came in the late 1982. Astronomers Margaret Geller and John Huckrow were mapping galaxy positions across a large slice of the sky. They were not searching for anything in particular. They simply wanted to see how galaxies were distributed in space. When the data appeared, it was shocking. Instead of a scattered distribution, they saw a colossal band of galaxies stretching hundreds of millions of light-years across space. This structure later became known as the CFA2 Great Wall, measuring roughly 500 million light-years in length, about 300 million light-years in width, and only about 15 million light-years thick. That number, 15 million, is critically important. It shows that the Great Wall is not a dense, bulky mass, but more like a thin sheet, spread across space. From the very beginning, this suggested that large-scale structures do not form as spherical clumps, but as extended planes and filaments woven into the cosmic web. For a time, the CFA-2 Great Wall was considered the largest structure ever discovered. But science rarely stops at the largest. As sky surveys grew deeper and broader, even larger structures began to emerge from the data. In 2003, using data from the Sloan Digital Sky Survey, astronomers announced the discovery of the Sloan Great Wall. This structure stretches about 1.37 billion light-years, nearly 3 times longer than the CFA-2 Great Wall. Light takes more than 1 billion years to travel from one end to the other, a number that made even seasoned scientists pause. The Sloan Great Wall is not only larger, but also more complex. It is not a single straight band, but a network of clusters and filaments linked together in ways that are difficult to describe using familiar geometric shapes. Almost immediately, a key question arose. Is this truly a physically connected structure, or simply several nearby structures seen from a particular viewing angle? This question is crucial, because in the universe, positional coincidence can deceive us. When 3-dimensional space is projected into 2-dimensional data, unrelated structures can appear connected. Distinguishing a genuine structure from a chance alignment is one of the greatest challenges in large-scale astronomy. In the years that followed, the list of largest candidates continued to grow. The Saraswati supercluster, announced in 2017, spans roughly 650 million light-years and lies about 4 billion light-years from Earth. The South Pole Wall, discovered in 2020, stretches at least 4 billion light-years, but resides in a region of the sky that is difficult to observe because it is obscured by gas and dust from the Milky Way. Each new discovery triggered 2 parallel reactions. On one side was excitement, because these findings expanded the cosmic map in unprecedented ways. On the other was caution, because the larger a structure appeared, the closer it came to the limits that cosmological models predicted were possible. No structure illustrates this tension more clearly than the Hercules Corona Borealis Great Wall. Announced in 2013, based on the distribution of gamma-ray bursts, this structure was proposed to extend up to 10 billion light-years. If true, it would occupy a significant fraction of the observable universe. From the outset, however, the Hercules Corona Borealis Great Wall was intensely controversial. Gamma-ray bursts are rare events and unevenly distributed. Some scientists argued that the sample size was too small to support claims of a continuous structure. Others suggested it could simply be multiple independent structures coincidentally aligned along the same line of sight. This debate was not just about one specific structure. It touched on a deeper question. At what point can we legitimately call something a structure? Must a structure be physically connected, with matter flowing between its parts? Or is a statistical pattern in the data sufficient? In modern astronomy, the answer increasingly favors the former. A real structure must be confirmed through multiple independent methods: galaxy positions, velocities, hot X-ray emitting gas, gravitational lensing, and large-scale matter flows. Relying on a single type of data carries a high risk of misinterpretation. For this reason, although the Hercules Corona Borealis Great Wall is frequently mentioned in popular articles, it has never been regarded as a securely confirmed, physically connected structure. It exists as a possibility, a suggestion, but not as a firm milestone in scientific understanding. Meanwhile, standard cosmological models make a key prediction. On sufficiently large scales, the universe should become homogeneous and isotropic. This is known as the cosmological principle, and it underpins most modern models. Put simply, if you zoom out far enough, No structure should stand out too prominently. This principle does not say that large structures cannot exist. It says that such structures must be rare and cannot extend indefinitely. There is a natural limit, set by the age of the universe and the speed at which gravity can gather matter before cosmic expansion pulls everything apart. This is why every new Great Wall discovery forces scientists to re-examine their assumptions. If a structure is too large, too coherent, and too common, it raises the question of whether the cosmological principle itself needs adjustment. So far, the principle has held, but not without small cracks. Against this backdrop, the scientific community entered the 2022 with a mix of curiosity and caution. Observational tools were improving. Data volumes were increasing, but the standards for announcing a largest structure ever were becoming ever stricter. It was no longer enough to say, "It looks big." Then, in early 2025, a new discovery was announced, one that differed fundamentally from many before it. It did not rely on a single type of data. It did not depend on chance alignments. Instead, it was based on hot, X-ray emitting gas, galaxy clusters, and clear physical connections between components. The name of this structure was Quipu. But to understand why Quipu is different, and why it is considered the largest physically connected structure ever confirmed, we need to look closely at how it was discovered and how it passed tests that previous Great Walls could not. That story does not begin with dramatic images, but with faint, blurry maps of the X-ray sky. There is a special moment in science when humanity believes it has nearly completed the big picture, not because every question has been answered, but because the overall framework seems solid. The pieces fit together, theories reinforce one another, and major observations fall within what can be explained. Cosmology, in recent decades, has occupied such a moment. We know the universe is expanding. We know it is composed primarily of dark energy and dark matter. We know galaxies are not randomly distributed, but arranged into a vast network known as the cosmic web. And most importantly, we believed we understood the limits of how large cosmic structures could be. That confidence rests on a foundational idea known as the cosmological principle. It states that if you observe the universe on sufficiently large scales, no place is special. The universe has no center, no preferred direction, and statistically, it must be homogeneous and isotropic. This does not mean the universe looks identical everywhere, but that large differences eventually average out when viewed on broad enough scales. Galaxies may cluster, but they cannot form structures beyond a certain limit. From this principle, modern cosmological models, especially the lambda CDM model, derive an important prediction. There is a maximum scale for structure formation. Gravity needs time to pull matter together, and the universe has a finite age, about 13.8 billion years. You cannot build a city without enough time to lay each brick, and you cannot build a structure billions of light years long if gravity has not had time to pull its components together. For this reason, scientists believed that galaxy walls, a few 100 million, or even just over 1 billion light years long, were already near the upper limit. For many years, major discoveries hovered around this boundary. Structures like the CFA, Great Wall, announced in 1989 at roughly 500 million light-years long, caused shock but remained theoretically acceptable. In 2003, the Sloan Great Wall, stretching about 1.37 billion light-years, forced many to recalibrate their intuition. But it still did not break the theoretical framework. Even more controversial structures, such as the Hercules Corona Borealis Great Wall, proposed in 2013 with a size of tens of billions of light-years, were ultimately met with serious doubt due to the lack of evidence for true physical connectivity. And then, in that context, Quipu appeared. Quipu was not discovered through a dramatic flash of light or a strange new galaxy in an optical telescope. It emerged quietly, through years of accumulated X-ray data from all sky surveys. Instead of visible light, astronomers focused on faint X-ray emitting regions, signatures of gas heated to tens of millions of degrees, drifting between galaxies inside galaxy clusters. This gas, not stars, is the true glue of large-scale structures. When the X-ray maps were overlaid and compared with distance data, a pattern gradually emerged, not a single cluster, nor a handful of isolated ones, but 68 galaxy clusters stretched across an immense region of space, connected by faint bridges of hot gas. These bridges were not optical illusions or chance alignments. They were real, physical structures, held together by the underlying network of dark matter. The total length of this system reaches about 1.4 billion light-years, with an estimated mass of roughly 200 quadrillion times the mass of the Sun. That number is so vast, it is almost meaningless to human intuition. If you tried to count to 200 quadrillion, one number per second, it would take more than 6 billion years, nearly half the age of the universe, just to say them all. But what makes Quipu extraordinary is not only its size or mass, but its physical coherence. This is not a random collection of galaxy clusters lying close together on the sky. It is a structure whose components truly interact gravitationally, participating together in a shared cosmic flow. The name Quipu is borrowed from the knot-based recording system of the ancient Inca civilization, and it is an unusually precise metaphor. If you imagine each galaxy cluster as a knot, then the strings connecting them are the filaments of the cosmic web, formed from dark matter and hot gas. Seen from a distance, the structure resembles a vast network of roots spreading through space, with dense junctions and thin branches extending hundreds of millions of light-years. This raises an uncomfortable question for cosmology. How could a structure like this form within the time the universe allows? According to current simulations, the growth of large-scale structure slowed dramatically around 5 billion years ago, when dark energy began to dominate and accelerate the expansion of space. Before that point, gravity was winning, pulling matter together and allowing clusters to grow. Afterward, the process became far more difficult. Quipu appears to have made it in time before that window closed. Light from its most distant regions left when the universe was already more than 13 billion years old, meaning the entire structure had to assemble within a relatively short span compared to its scale. This does not violate the cosmological principle, but it forces us to refine a critical question. At what scale does the universe truly become homogeneous? That threshold may be larger than we once believed, or the initial conditions of the universe may allow for rare but statistically valid exceptions. One key reason the scientific community considers Quipu confirmed, unlike some earlier controversial structures, lies in the method of detection. Structures such as the Hercules Corona Borealis Great Wall were inferred primarily from the distribution of gamma-ray bursts, rare events with uneven coverage and strong observational biases. Quipu is different. It is seen through X-ray emitting hot gas, which constitutes a major fraction of the baryonic mass in galaxy clusters and directly traces the underlying gravitational potential. In other words, Quipu is not merely a visually striking pattern on a map. It is a physical entity that exists, actively holding galaxy clusters together within a shared gravitational relationship. Each of the 68 clusters involved is itself a cosmic city, containing hundreds to thousands of galaxies, each galaxy hosting billions of stars and countless planets. When all these layers of structure are stacked together, the scale becomes almost absurd. a structure built from components that already lie far beyond any human frame of reference. Quipu also forces us to re-examine numerical simulations of the universe. In many large simulations, structures similar to Quipu are not forbidden, but they are extremely rare. Finding one within a region of space that is relatively nearby, by cosmic standards, raises a difficult question. Were we simply lucky? Or are our models still missing something? The answer could lie in how dark matter behaves on very large scales, or in how initial density fluctuations were distributed shortly after inflation. One thing, however, is certain. Quipu is not an endpoint, but a punctuation mark. It marks another moment where human intuition is overtaken. Just as when we first realized Earth was not the center of the universe, or when we discovered the universe was not static but expanding, Quipu reminds us that whenever we believe the big picture is complete, the universe quietly reveals another layer. And here, the sense of awe returns. Not awe driven by raw numbers, but by the realization that even the limits we consider solid are provisional. Quipu exists as a reminder that the universe has no obligation to fit human intuition or human models. It only needs to obey physical laws. And sometimes, those laws permit structures so vast that we are forced to pause, take a deep breath, and admit that we are still standing very close to the edge of what can be understood. As the initial shock of Quipu fades, what remains is no longer the feeling of unimaginable size, but a quiet, unavoidable question. Does this structure truly fit within what we believe about the universe? In science, some discoveries are satisfying because they confirm what we already know. Others do not immediately break any theory. They simply stand there, silently, forcing us to reconsider the entire framework. Quipu belongs to the second category. It does not declare the current cosmological model wrong, but it pushes that model to its limits. For nearly a century, modern cosmology has rested on a core assumption known as the cosmological principle. This principle states that when observed on sufficiently large scales, the universe looks the same in every direction and at every location. No center, no preferred region, no statistically special place. Galaxies may cluster, clusters may link into networks, but when you zoom out far enough, these differences should average out. This is not a vague belief. It is the foundation of how we describe the universe's history and structure. From this principle, structure formation models derive a crucial consequence. There is a limit to how large cosmic structures can grow. The reason is not spatial size, but time and speed. Gravity is not instantaneous. It requires billions of years to gather matter, slowly, against the expansion of space. A universe that is 8 billion years old simply does not have enough time to build structures beyond a certain scale, at least according to current models. For many years, the largest discoveries fit comfortably within that limit. The Great Walls, found in the late 20th and early 21st centuries, were enormous, but explainable as rare yet valid fluctuations in an otherwise homogeneous universe. Even when they unsettled human intuition, they did not destabilize the theoretical framework. Crucially, these large structures were treated as statistical outliers, not as signs that the model lacked a fundamental ingredient. Quipu appears precisely at that fragile boundary, with a length of about 4 billion light-years and a mass approaching 200 quadrillion times that of the Sun. It is not the largest structure ever proposed, but it is the largest structure confirmed to be physically coherent. That changes the nature of the question. The issue is no longer whether we are being fooled by projection or perspective, but whether a structure like this should exist within the limits imposed by current theory. The key lies in the concept of a coherent structure. Quipu is not merely a chain of clusters close together on the sky. It is a system in which clusters are connected by filaments of dark matter and hot gas, participating together in a shared gravitational field. X-ray data show that the gas between clusters is not randomly distributed, but stretched into faint bridges, evidence that matter has had time to flow and settle into these connections. This detail is what makes Quipu difficult to ignore. In numerical simulations, such structures are not strictly forbidden. They exist at the extreme edges of probability. Rare, but possible. Their rarity, however, depends sensitively on initial assumptions. The amplitude of density fluctuations after inflation, the properties of dark matter, and the universe's expansion history. Finding a structure like Quipu within a region of space we have already surveyed relatively well forces cosmologists to ask whether we have correctly estimated just how rare such structures should be. This is not like discovering a new particle or an entirely unexpected phenomenon. It is more like remeasuring a bridge and realizing it is carrying load very close to its design limit. The bridge still stands, but you cannot help rechecking the assumptions that went into building it. In this case, the bridge is the lambda CDM model, and the load is the existence of extremely large structures like Quipu. Another source of tension is timing. Light from the clusters in Quipu shows that the structure already existed before the universe reached its current age. That means its assembly had to occur during the era when gravity was still strong enough to counter expansion. Had Quipu formed even slightly later, or had its filaments been less tightly connected, the story might have been different. Its existence suggests the universe used nearly the full window of opportunity available for building large structures. It is important to emphasize, however, that there is no evidence that the current cosmological model is wrong. Measurements of the cosmic microwave background, large-scale galaxy distributions, and the expansion history of the universe remain consistent with model predictions. Quipu does not directly contradict any foundational observation. Instead, it serves as an extreme stress test, forcing models to demonstrate that they can produce rare but permissible structures. For this reason, the scientific response to Quipu has not been rejection or panic, but refinement. New simulations are being run at higher resolution. Surveys are being extended to determine whether Quipu is unique or merely the first clearly resolved example. Hypotheses about dark matter, especially how it distributes and interacts on the largest scales, are being examined more carefully. This is how science advances, not through constant revolutions, but by repeatedly testing the boundaries of what is believed to be true. From the observer's perspective, something subtle but important shifts. Before Quipu, the largest cosmic structures could be treated as highlights within an otherwise stable picture. After Quipu, the picture does not collapse, but it becomes more dynamic, less certain. The boundary between what is normal and what is rare but valid blurs, and it is often within that blurred region that science finds its most interesting questions. This is where the line of thought naturally turns. Faced with a structure large enough to strain theoretical limits, the next step is not only measurement and simulation, but imagination. Not poetic imagination, but conceptual imagination. To understand what those dry numbers truly represent, one must ask what it would be like to exist within such a structure. If Quipu truly spans billions of light years, if its galaxy clusters are separated by tens or hundreds of millions of light years, what would it mean to travel through it? This question does not replace science with emotion. It bridges two ways of understanding, equations and intuition. And from this tension, from the boundary where the model still holds but is stretched to its maximum, the narrative naturally shifts direction. Instead of viewing Quipu as an object on a map, we attempt, if only in imagination, to step inside it, set aside diagrams, maps, and graphs for a moment, and imagine something almost impossible. You are no longer looking at Quipu as a bright trace on a computer screen. You are standing at its edge. No telescope. No data. Just you and a space so vast that familiar notions of near and far begin to lose meaning. Before you is not a continuous wall of galaxies, but a sparse region of space where galaxies appear as isolated islands, separated by immense distances in a black ocean. Suppose you had an impossible vehicle, one that could instantly accelerate to the speed of light without being constrained by known physics. Even with that unreal assumption, the journey does not become easier to grasp. You begin moving into Quipu, and for the first several 100,000 years, almost nothing changes. Space remains empty. The cold cosmic microwave background surrounds you, and only occasionally does a faint spiral galaxy drift through your field of view like a solitary spark. After about 1,000,000 years, you realize you have still not traveled very far by the standards of this structure. On Earth, 1,000,000 years is enough for species to evolve, for ice ages to come and go, for entire ecosystems to vanish and be replaced. Here, 1,000,000 years merely marks the moment you have left the outer edge of a thin filament. Quipu does not reveal itself through density, but through the merciless patience of distance. As you continue deeper, the filaments begin to resolve more clearly. They are not bright, glowing strands like those in illustrations, but regions of space where the density of galaxies is only slightly higher than the surroundings. You can travel tens of millions of light years along a single filament, encountering galaxies one by one, each containing hundreds of billions of stars. Yet the distances between them remain so vast that any notion of closeness becomes meaningless. After roughly 10 million years of travel, you encounter your first galaxy cluster. This is where the landscape truly changes. Hundreds of galaxies appear within a relatively compact region, moving chaotically around a shared gravitational center. Hot gas fills the space between them, invisible to the naked eye, yet accounting for most of the cluster's baryonic mass. If you could see in X-rays, the entire region would blaze intensely, like a colossal cloud heated to tens of millions of degrees. You pass through this cluster over the next few million years. During that time, on Earth, if Earth still exists, continents would have shifted, mountain ranges would have eroded and risen again, and countless species would have appeared and gone extinct. But for you, this is just a brief segment of the journey, a highlight within a network that still stretches almost endlessly ahead. Leaving the cluster behind, you return to sparse space. Filaments continue onward, sometimes branching, sometimes intersecting, forming intricate nodes. You begin to realize that Quipu has no simple path from beginning to end. It resembles a vast root system, where every direction leads to a different part of the structure. Yet no path can truly be called the center. After about 100 million years of travel, you have covered only a small fraction of Quipu. 100 million years. On Earth, enough time for dinosaurs to dominate and vanish, for mammals to rise from tiny creatures to ecological prominence. Here, you are still near the outer regions of the structure. Quipu is not only vast in space, it consumes time as well. As you continue, galaxy clusters appear more frequently. Some are in the process of merging, their hot gas colliding and generating shock waves that propagate across millions of light years. You traverse such regions over tens of millions of years, witnessing some of the most violent events since the Big Bang. Yet everything unfolds so slowly it feels almost static. These collisions are not brief explosions, but processes that stretch across billions of years. After roughly 500 million years of travel, you realize you have covered only about 1/3 of Quipu's length. On Earth, 500 million years is enough for complex life to first erupt during the Cambrian explosion, for oceans to change their chemical composition, for atmospheres to transform multiple times. Along your journey through Quipu, it is merely a stretch of road. As you approach the central regions of the structure, the density of galaxy clusters increases noticeably, filaments grow shorter and thicker, and the junctions more complex. If you could see dark matter, you would observe a tangled network enveloping everything, dictating the trajectories of every galaxy and every cloud of gas. You are no longer moving between isolated islands, but through a genuinely connected system. After about 1 billion years of continuous travel at the speed of light, you begin to glimpse the far edge of Quipu. The light from the clusters behind you has changed, because during your journey, they themselves have evolved. The brightest stars have died, clusters have merged further, and the structure you are leaving is no longer identical to the one you entered. You have traveled not only through space, but through a thick slice of cosmic history. Finally, after roughly 4 billion years, you emerge from Quipu. Ahead lies sparse space once more, vast voids where the number of galaxies drops sharply. Behind you is one of the largest structures ever to exist, a network of thousands of galaxies, trillions of stars, and countless worlds that will never meet. If you turn back, you cannot see Quipu in its entirety, because there is no position from which it can be viewed all at once. This thought experiment is not meant to make Quipu more mystical, but to restore something that numbers tend to erase: a sense of true scale. A structure 4 billion light-years long is not just a large number. It is a span of time longer than the entire complex history of life on Earth. When we talk about Quipu, we are not only talking about size, but about whether the universe had enough time and enough patience to build something so far beyond human intuition. And it is precisely here, as you step beyond the far edge of Quipu, that another realization begins to form. If traversing a single structure requires more than 1 billion years, then what we observe from Earth cannot possibly be a snapshot taken at one instant. Every part of Quipu we see must belong to a different moment in cosmic history. The structure, as we observe it, does not exist at a single point in time. This thought does not end the journey. It opens a deeper, subtler question. When we observe Quipu from afar, how are we seeing it in time? And if time itself is stretched along the length of the structure, what does the picture we draw truly represent from here? The line of thinking naturally shifts, from a journey through space to a journey through time. Even in imagination, traveling through Quipu leaves a strange impression, not of distance, but of time. As you move from one galaxy cluster to the next, there is no ticking clock, no marker announcing that you have crossed into a new moment. Yet in reality, with every step forward, you are moving deeper into the past. Not metaphorically, but in the strict physical sense. Light does not reach us instantly. It requires time to cross space. And on cosmic scales, that time is no longer a detail we can ignore. When you look at a star a few light years away, you see it as it existed years ago. When you look at a galaxy millions of light years away, you are looking back to a time when humans did not yet exist. And when you look at a structure stretching billions of light years like Quipu, you are no longer observing a single moment, but a time span extending hundreds of millions of years. This leads to a consequence our intuition struggles to accept. Quipu, as we observe it, has never existed in its entirety at any single instant. There was no moment in cosmic history when everything we see on the Quipu map simultaneously had that exact form. The nearer parts of the structure sent their light when the universe was significantly older than when the light left its farthest regions. the galaxy clusters at opposite ends of Quipu, in our observations, inhabit different eras of the universe. If you try to imagine Quipu as a static object, like a mountain range or a continent, you will always misunderstand it. It is not a solid shape frozen in space, but a picture assembled from many slices of history. Each galaxy cluster is a memory of the universe at the moment its light departed, and those memories are not the same age. This temporal stretching becomes especially pronounced for a structure about 4 billion light-years long. The light travel time difference between its near and far edges can reach hundreds of millions of years. During that interval, the universe does not stand still. Galaxy clusters continue to merge. Filaments continue to draw in matter, and the expansion rate of space evolves under the influence of dark energy. When we map Quipu, we are therefore placing different versions of the structure side by side. This also explains why scientists must be extremely cautious when speaking about the shape or state of immense structures. A cluster on Quipu's far edge may appear chaotic, rich in hot gas, with clear signs of ongoing mergers. A cluster nearer to us may appear calmer, more dynamically relaxed. Both descriptions are correct, but they do not refer to the same moment in time. In this sense, Quipu is not merely a structure in space, but a historical record of cosmic structure formation. When we observe it, we are seeing different stages of the same physical process, arranged not by time, but by distance. This makes understanding Quipu both richer and more difficult. Richer, because it allows us to study how galaxy clusters evolve without waiting hundreds of millions of years. More difficult, because we must constantly remind ourselves that no detail in this picture represents the present of the entire structure. Everything is the past, differing only in how far back. Even the concept of a coherent structure must be understood this way. When we say Quipu is physically connected, we are not claiming that all its components are interacting in the same dynamical state at this very moment. We mean that across the span of history we observe, the galaxy clusters show a consistent gravitational linkage, maintained by filaments of dark matter and hot gas. That coherence exists through time, not within a single instant. Returning to the imagined journey through Quipu makes this even clearer. During the time it takes you to travel from one end to the other, the structure itself changes. Some clusters you pass may have completed major mergers long ago, while others, farther away in light travel time, are still in turbulent phases. You cannot say you have seen Quipu as it is, because there is no such moment to see. From Earth, the situation is even more extreme. We do not move through the structure. We remain still and allow light from its different regions to arrive over time. The map we construct is the result of stitching together signals that originate from different moments in cosmic history. Calling it a spatial map is only half correct. The other half, inseparable from it, is a map of time. This also changes how we perceive size. When we say that Quipu is 4 billion light-years long, we are not only talking about the distance light must travel, but about 4 billion years of history compressed into our field of view. Each point along the structure represents a different moment in the universe's evolutionary process. And then, a deeper realization begins to emerge. This is not unique to Quipu. The entire universe we observe operates according to this principle. Every galaxy, every star cluster, every structure, large or small, is seen through the lens of time. We never see the universe as it is right now. We only see what the universe once was. For smaller structures, this does not significantly alter how we understand them. But for colossal structures like Quipu, time differences become decisive. They force us to abandon the idea of a static picture and accept that what we are observing is a process, not an object. And at this point, the line of thought naturally shifts to another question. If what we see is already the past, if the largest structure we know is observed through such a thick layer of time, then what lies ahead for it? Not the image we observe, but its true fate in a universe that continues to expand. Once we view Quipu as a structure extended across both space and time, the original question becomes clearer and no longer concerns size alone. Largest here does not simply mean how many light years it spans or how many galaxies it contains, but the degree to which a structure can maintain physical coherence in a universe that is relentlessly expanding. Quipu is not the largest because it looks overwhelming on a map, but because it still exists as a physically meaningful system at a scale where everything should, in principle, have fragmented into disconnected pieces. In a universe where dark energy dominates and space expands ever faster, the fact that galaxy clusters remain linked by filaments of dark matter and hot gas is far from obvious. On small scales, gravity prevails. On extremely large scales, cosmic expansion begins to dominate. Quipu sits precisely at that fragile boundary. It is evidence that gravity can still organize matter into a continuous structure at scales we once believed were too large. Therefore, when we say Quipu is the largest structure ever discovered, we do not mean it is the largest that could possibly exist. It is the largest that we can confirm as a physically connected entity, rather than a chance alignment of galaxies along our line of sight. This distinction sets it apart from earlier, controversial records, and explains why Quipu is regarded as a milestone rather than just another large number on a list. But the more important insight lies elsewhere. Quipu shows us that even in a universe being stretched and diluted by dark energy, there remains a memory of structure formation. The filaments connecting galaxy clusters are not merely channels for matter, but traces of how the universe evolved from minute density fluctuations in its earliest moments. At the largest scales we have ever observed, order has not entirely vanished. Seen from a broader perspective, Quipu does not diminish humanity in any negative sense. On the contrary, it demonstrates an extraordinary human capacity. From a very ordinary planet, orbiting an unremarkable star, we can infer, measure, and understand structures spanning billions of light years. The largest structure ever discovered in the universe is not only something out there, it is also the farthest boundary that human thought has reached so far. And perhaps that is why Quipu truly matters. Not because it concludes the story of the largest structures, but because it reminds us that the universe remains ordered enough to be understood, and vast enough to continually raise new questions.